Welcome to Frontline Systems webinar on an overview of simulation applications in Excel using our advanced products. My name is Dr. Sima Maliki. I am Consulting Lead and Modeling Specialist at Frontline Solvers. During this presentation, if you have any questions or comments, please type them to the chat box to be answered at the end as time allows. I strive to remain within the promised time frame, yet to thoroughly cover all the material, sometimes it takes a few minutes longer. I very much appreciate your cooperation. As we all know, the Monte Carlo simulation and risk analysis techniques are widely used across many industries and functional areas. These are just some of the examples: energy and utilities, chemical, manufacturing, transportation, financial services, and at the right side you can see some of the applications: currency valuation, retirement planning, pricing, and so on. Now let's talk about some of the reasons. Almost every business outcome has some uncertainty. Uncertainty can impact our decisions and actions in desirable as well as undesirable ways. If we own shares of stock, the future price is uncertain. It may go higher, which is desirable, or it may go lower, which is undesirable. Furthermore, you might be concerned with the future demand for your product, for your production variations, delivery lead time, or future interest rates. The main point is that when there is significant uncertainty, expected case or average estimates are typically wrong. When you have multiple uncertain factors affecting your business situation, what-if analysis is very likely to be insufficient. That is because it won't capture all the outcomes, and you may be surprised by the real outcome, although you have considered a best, worst, and average case. However, the good news is you can model risk and quickly quantify the full range of possible outcomes. Risk analysis helps recognize the difference between the expected value of a decision alternative and the payoff that may actually occur. This tool allows you to graphically show the range of possible outcomes and very often reveals other valuable insights to you, to your management and stakeholders. In fact, we have seen over and over that risk analysis skills are a career enhancer for our users for several reasons. First of all, you see that as we perform further analysis by doing sensitivity analysis, you will get a good sense for what factors really matter in these business situations with uncertainty. If you are negotiating with another party and you have done your homework with risk analysis and they haven't, you have just given yourself a significant competitive advantage. And finally, as you rise in the ranks of a company, the decisions start to involve more and more uncertainty, and so the skills involved in coping with uncertainty and modeling it realistically become more and more important. Today, we explore how risk analysis and Monte Carlo simulation can benefit you in solving your business problems in uncertain situations, and how easy it is to use Frontline Systems tools such as Risk Solver Pro and Risk Solver Platform to model and manage those problems. Together, we review typical applications including inventory management with uncertain demand, manufacturing with uncertain processing times, and revenue management application in an airline with uncertain number of no-shows. Then we'll discuss decision trees and using simulation optimization to optimize your decisions under risk. Now, it is time to dive in and see how we can use the Monte Carlo simulation in practice. One of the key decisions in manufacturing, retail, and some service industry businesses is how much inventory to keep on hand, making sure you can come through on the promises to your customers. In general, we need to have a dedicated balance between three classes of costs: ordering, holding, and shortage or lost opportunity costs. So let's find out in this example how simulation can be used to understand the range of possible outcomes for total costs. I'm going to open the Excel workbook that is ready for us, and we are going to review it all together. Just before that, let me walk you through our tool and some of the features that we will be using. On the ribbon, you can see we are using Risk Solver Pro. This is our Monte Carlo simulation product. Let's review the ribbon together. As you can see, if I click on this Model tab, it displays or hides the task pane. In the Simulation Model tab, you can have access to different components of your simulation model to set up your models. This includes the Distribution button to access a range of predefined probability distributions that you would use to represent your uncertain variables. And then you can use correlation to define correlation between your uncertain variables, and you can use the result button to compute statistics, risk measures, and range values for your uncertain functions, and you have the Six Sigma matrix. Then in the parameters tab, here you can have options to run multiple parameter simulations, and we will practice using this parameter simulation in one of the examples in the yield management model. Solve Action tab allows you to run simulation models. In the Analysis tab, you can analyze the results, create reports and charts. And then in the Tools tab, you can create decision trees, fit distributions, verify simulation results, change number of tries, and then there's this Publish button that allows you to publish your models for use and distribution on the web. So there's some other options here, and then we have Help tab. Here you can display online help, open examples, user guides, online tutorials, and access your license status and more. Now the right side, this is called the task pane. I'm going to increase the size. First tab is Model tab. Here you can see there's a simulation, and then we have uncertain variables, uncertain functions, a statistic function, and if you have parameters, we can see them here. So here you can view the model in outline form, and you can optionally edit model elements in place. For example, if I select like one of these decision variables, you can see here you can change the formula and you can change the parameters. Next is Platform tab. Here you can view or change the platform options, such as number of simulation to run. This is 1. Trials per simulation. This is 1,000. And we will discuss this in more detail today. So don't worry about all this detail. Just want to show you what is available. And next is Engine tab. Here you can review and select simulation options for Risk Solver engine. What would it mean? So for example, we have the sampling method, random number generation. These are the things that you can change about what methodology do you want for your risk solver engine to create your Monte Carlo trials. And then the last one is Output tab. It allows you to view a log of simulation messages. Now back to our example. So this is an inventory management example. And we want to see how we can use simulation to understand the range of possible outcomes for our total costs of inventory. So here is the beginning inventory at the beginning of first week. So this is for week 1, and then we have the beginning inventory. And then this amount of shipment received, and then our weekly demand for our product is uncertain. This is our uncertain variable. And here we have used a Poisson distribution for estimating demand. I'm going to double click on this cell to show you this uncertain distribution, the Poisson distribution. This is called an uncertain variable dialog. You can see the PDF tab, CDF tab, and a chart of cumulative form of the distribution function, and then the reverse CDF. And at the right side, you can see in the drop-down menu, first is parameters tab. You can see the formula, you can see the parameter of this function, and other information. And then we have the statistic about this function, what is the mean, what is the variance, and then percentiles, and then chart types, other options that you can choose to change. You change chart settings and so on. So let me close this. Then we have other problem assumptions. The order quantity and the reorder point. We may receive shipment and we face a 2-week delivery lead time. As you can see, we have a fixed order quantity size. Then the ending inventory of this cycle would be the beginning inventory of next cycle. And based on all this information, we calculate total holding cost, order cost, and opportunity cost. And then here we calculate the total cost with this sum. Now I'm going to click on Simulate, Run Once. We just ran 1,000 Monte Carlo trials. You can see in the top, the number of trials is set to 1,000. On each trial, we have a different randomly sampled value for demand for every week. As you recall, for demand is uncertain, and we have used the Poisson distribution. Then, based on that, we calculated total cost of inventory. This frequency chart shows the distribution of all possible outcomes for our total costs. This shows us what happens for a specific policy of order quantity and reorder point. You can easily change the order quantity and reorder point and then rerun this simulation to see if there is a better outcome. And in this chart, we have the frequency, cumulative frequency, and reverse, and then you have this sensitivity tab displaying a tornado chart showing you which input has the most impact on the total cost. And then you can verify the scatter plots and so on. And again, at the right side, you have statistics, percentiles, and Six Sigma matrix, and so on. You can change your chart settings and so on. Let's go back to our slides and review a summary of what Monte Carlo simulation is. Monte Carlo simulation is a flexible technique for modeling a real system in which uncertainty is a key factor. It uses repeated random sampling to represent uncertainty. With appropriate sampling, outputs are representative of results from all possible combinations of uncertain inputs. And then, for a given decision, which are values of inputs under your control, simulation describes the outcomes and the possibilities that these outcomes will actually occur. Now, let's look at another application. This is a small parts manufacturing example. This is very simple, and I'm going to show you how you can actually add the distribution to the example. So, this is about a machine component that is to be manufactured at a production shop. And it requires two different processes, drilling and grinding, which are uncertain. The goal is to calculate the number of components that could be manufactured in a workday consisting of 8 hours. Let me open the workbook. So here's the workbook. The processing times for drilling is modeled. As you can see, I hover over it and you can see it is the sine normal distribution in cell C2. Let me show you the distribution function. So it's a sine normal, and we can see we have used this side truncate distribution. Why? The processing times can never be less than 0. So here we have used the side truncate to restrict the drilling time to be always greater than 0. But there is an easier option to do this. Let me show you how you can select an empty cell, for example, and then to add a normal distribution, click on Resolve Pro, click on Distributions, Common, and then choose Normal. The Add Distribution dialog opens, and then here we can adjust the mean and standard deviation. To make sure that we never get values less than 0, instead of using side truncate function, there is an easier way, and that is lower cutoff values. So instead of negative infinity, I can change that to 0. And click on Save. You can see the impact. If I click Save, you can see this distribution is added here. And it's the same way, it's just a sine normal, but different parameters, and I just want to show you how you can actually add a distribution. So I'm going to delete this distribution, as we already have the actual normal distribution that we're using to model our uncertain drilling times. So that in the model tab, you could just right click and click on Delete. Now the processing time for grinding is modeled in cell C3. And you can see we have used a log logistic function. Let me double click. Then we are calculating the total number of components produced in a workday consisting of 8 hours. To calculate the expected or average number of components manufactured, you can use the SciMin function. To use the SciMin function, first you have the formula to calculate the total number of components, and then to calculate the expected or average value, you can go to Results button, go to Statistics, and choose Mean. And then refer to the cell that actually calculates the value for you. And then we have the standard deviation function to calculate the standard deviation of number of components produced in a day. If you want to know the chance of producing at least 50 components a day, you can calculate this using the SciTarget function. And you can see we are pointing to C8, which is number of components produced, and then 50. Okay, so we are ready to run one simulation. Let's click on Simulate, Run Once. And here are the results. Here is the histogram of the number of components produced. You can see the mean is about 41. Let's go back to our slides. Next, let's look at an airline revenue management example. We are going to do different things about this example. We are going to use historical data to fit a distribution. We are going to use parametric simulation. At the end of the webinar, we are going to apply simulation optimization, meaning we use the power of optimization to solve this problem. So there are people that have tickets on a flight and will not show up, and they like to reuse those tickets on a subsequent flight. So there is always an incentive for airlines to overbook a flight. Here we are looking to understand the range of possible outcomes for total revenue given what can happen with no-shows. Let's review the model in Excel. Here is the model. As you can see, this flight has a capacity of 100 seats, and then the tickets are 200 per seat. Then you can see the assumptions for refund to no-shows and overbooking compensations. So the uncertain quantity in this model is the number of no-shows. So we need to model this with an uncertain variable. In C7, we are estimating this number with a sine log normal distribution, and we are rounding it in cell C6 for the total number of people. Let me double click on this cell for our uncertain variable, which is number of no-shows. You can see this is a sine log normal distribution. Here, number of tickets sold, and we calculate total revenue here. So based on number of tickets sold, number of overbooked tickets, and refunds to no-shows and overbooking compensations. So that would give us our total revenue. In cell C16, again, we are using the sign-in distribution for calculating the expected total revenue. Here, we have this distribution, the Silog normal, for our number of no-shows. You might be wondering how would we arrive at an appropriate distribution for number of no-shows or your uncertain variables in general. For an airline, here we have some historical data. This might apply to your business situation as well, if you have historical data. Here is the historical data on the number of no-shows from different occurrences of this flight. Now we are going to fit an analytical distribution to this historical data, and then we try to use that analytical distribution the best way in the model. If you are not sure what distribution to use, you can always use Distribution Wizard to help you choose an analytic distribution that fits the historical data. Let me show you how. So I'm going to first select the data. I find it more easy. So then click on Distribution Wizard. And you can use this Distribution Wizard even if you don't have historical data. You can see, do you have some historical data or observed data for this uncertain variable? If we say no and click on next, then it will give us some more information, ask us, oh, if in this uncertain variable is a discrete, continuous, and then helps you find and choose a proper distribution. You can see it's a step-by-step help. But let's go back because we have historical data. So when it's asking us, do you have historical data? Yes, let's say yes. We need to enter or select the range of cells containing the values. Since I've initially selected the data, you can see it automatically identifies the range of observation. Otherwise, if you didn't, you can just click on this button and select the cells. Now let's click on next. Here it is asking if our data is continuous or discrete. I am going to choose continuous. This is just for illustration purposes, and I'm going to override this selection. And then click on next. Here, now we have the option to choose to fit the data, use all the data using a zip function, or resample the data. I'm going to choose to fit the data, fit an analytical distribution to this data. Let's click on next. Now you can see the fit option dialog appears. There was an easier way if you're really familiar with everything, you didn't know, and you didn't need to go through the distribution wizard. You can just click on fit option on the ribbon in the tools tab next to decision tree at the right side. Okay, here in this fit options dialog, let's choose that our data is continuous again. We are going to keep all the default settings and click on fit. Here, Risk Solver computes and displays a ranked list of candidate fitted distributions, and you can see the results here. This ranked list of candidate distributions that fit our data, and you can see that the best one is Silog normal distribution, and that is the best fit to our historical data. So let me show you. For example, you can choose other one and just compare all of them together. And the different options here. So about this log normal distribution that is the best fit to our data, you can see that the mean is about 10 tickets and the standard deviation is about 6, meaning 6 tickets out of 100 tickets. That is our flight capacity. So this is based on the number of tickets sold, 100 tickets, and we are not overbooking. In a minute, we are going to change that assumption and allow more tickets to be sold. So what we are going to do, we are going to overbook our flight. So what does that mean for the number of no-shows? If we think about it, as we sell more than 100 tickets, we expect the number of no-shows to go up as well. So we won't use this fitted distribution as is. Instead, we want to create a distribution that depends on the number of tickets sold. And that is what we have done in the workbook. So we are going to use the log normal distribution, but let me show you that how we have changed it. Do we wish to accept the distribution? Let's say no. So here is the Silog normal, as log normal was the best fit. Now let me double click and show you that. You can see the parameters of this distribution. For the mean, if you recall, it was about 10. Now we have used 10% of the number of tickets sold. And then for standard deviation, we have 6% of number of tickets sold. If you recall, for that fitted distribution, the standard deviation was about 6. So this is how we modified it. So it depends on the number of tickets that we sell. In cell C11, you can see C11 is number of tickets sold. Okay, let's just run one simulation. Click on Simulate, run once, and here are the results. We can see the total revenue and then expected revenue. And this is the histogram of our total revenue. And you can see I have a marker here. To add a marker, you can just go to the last option, markers, and just click on this plus button. You can change the colors and add a marker at the specific value that you need. It is natural to ask how sensitive the total expected revenue is to the changes in the number of tickets sold. To answer this question, Risk Solver has a capability to allow us to ask what if and run a new simulation on each change. To turn on this feature, which is called interactive simulation, you can simply click on this light bulb on the ribbon. You can see it will light up, and very quickly your first Monte Carlo simulation is complete. 1000 Monte Carlo trial. The default number will be executed each time we change the spreadsheet. Now we are ready to play what if with the simulation model we have. And we have this marker, we can use it as a reference point. This is about the 19,000 revenue point. It's a $19,000. So I'm going to manually change the value in cell C11, the number of tickets sold, and we can see the impact on total revenue and expected revenue. So let's try to sell 110 tickets and see what is the impact. Here are the results. We can see that the results show that the expected revenue in cell C16 went up. So on average, the balance between overbooking compensations and number of no-shows is working toward our favor. Now let's change the number of trials from 1,000 to 10,000. So in the top on the ribbon, I'm just going to add one more 0. So now 10,000 Monte Carlo trials will be done each time we change the spreadsheet. Okay, let's try, let me add the 0. Now let's try 120 tickets. So we are selling 120 more than our flight capacity. And here are the results. Well, looks like the expected revenue might have gone up. Now it is hard to tell if you have gone too far with 120 tickets or not, but let's try 130 tickets. Or 140. If you are seeking insights about what matters in this model, interactive simulation lets you explore that much the same way as an ordinary what-if spreadsheet. You can just ask what if with uncertainty, just like in the spreadsheet, and you are getting a new simulation every time you change the spreadsheet, where each trial is a recalculation of the spreadsheet. Now imagine you have done interactive simulation enough times to get used to it, but you would like to automate that. Now is time that we can use the power of parametric simulation. So you don't need to sit there and change the parameters yourself each time. Let me show you how. Let's first turn off the interactive simulation mode with clicking on the light bulb. Now we need to choose the number of tickets sold and define it as our simulation parameter. And then we are going to give a range of values to it and then see the results. So let's choose this, close this chart. Select the number of tickets sold and click on Parameters, Simulation. Okay, in this function argument for our parameter, which is number of tickets sold, to change it from 100 ticket to 150, for example, testing all values, let's choose 100 and then 150 for our upper bound. Now, to run one simulation once for each value of the parameter, this parameter that we have, number of tickets sold, we need to change the number of simulations. So, if you recall, we go to Platform tab. Here is the number of simulation. Instead of 1, I'm going to change it 51. The reason is with 51 simulation, I will be able to test all possible values of tickets sold between 100 and 150. We're going to run a simulation for 100 tickets, another one for 101, all the way to 150. Okay, so I changed the number of simulation. And since the number of trials is 10,000 trials, when we run this, we will be running 510,000 Monte Carlo trials. Let's click on Simulate, Run Once. And here are the results. You can see on the Output Report tab, you can see the results for each of the simulation. This is the frequency chart for simulation number 51. But you can look at each individual simulation results by easily changing the simulation drop-down selection in this chart and review the frequency chart for simulation number 45, simulation number 20, simulation number 1. Let me close this. Now, the worksheet will initially display values for the last Monte Carlo trial. Actually, before we change that simulation drop-down. So if you recall, I changed it to 1. So now it's showing the simulation number 1. But there is a way you can change it from here. So now it's on 1. Then you can go to 8. You can go to 40 and then see different values for each Monte Carlo simulation result. But you can also use the trial arrows and cycle through individual Monte Carlo trials. So we are on simulation number 40, and then you can click on these arrows to cycle through each of the 10,000 trials for that specific simulation. You could also look at all simulations together using one of the several reports or charts. Let's explore the charts. For example, if you want to see how the results varies across all 51 simulations, we can use the trend chart. Click on Charts, Multiple Simulations, and Trend. I'm going to click on the first button to select all 51 simulations and click OK. Risk Solver then draws the trend chart showing the behavior of our total revenue across all 51 simulations. Increase the size. This blue line is the mean value of revenue. And then you can see the 75 percentile and 90 percentile. And you can see that here are the parameter number of tickets sold as parametric values. We started from 100 all the way to 150. And you can see that as we sell more tickets, overbooking our flight, our revenue goes up, but eventually it peaks out because we are paying too much in overbooking compensations. So we can get some insight right now, and we can see that the best number of tickets to sell is something around 116, 117 tickets. We are going to leave this example here, and then later, after reviewing the decision trees, we're going to come back to this example and use the power of optimization in this problem with uncertain number of no-shows. So let's close this chart. Let's go back to our slides. This is a review of just what if with interactive simulation that we practice. This is just a summary of steps to apply the Monte Carlo method. You can start with constructing an ordinary what-if spreadsheet model as you have always done. Then you can identify your uncertain inputs and then you specify probability distributions, and remember you can always use that distribution wizard. Okay, now on to our next topic, decision trees. This is when you are faced with multiple stage decisions and uncertain outcomes at each stage. Decision tree would be the right choice for you to develop an optimal strategy. Building a decision tree is really easy, and all the details are available on the user guide, but there is a lot you can do with decision tree. So I'm going to show you an advanced application of decision tree in different scenarios, and I will show you that you can actually apply the power of simulation to your decision trees. We're going to review this together, and then for the details you can just refer to our user guide, or just feel free to, I will share you my email and you can ask me questions. This is about a firm owner that is considering whether or not to apply for an $85,000 research grant by submitting a proposal. So let's open the example together. And I will going to show you when you install one of the products, this is how you access all the available examples. Click on Help, click on Examples. So this workbook will open and it will give you access to all available examples. If you want to review Monte Carlo simulation, you click on this button. If for now we are going to click on decision tree examples, so just click on that. And the example we are going to review together is a grant decision analysis. And here is the tree. To increase the size. So this is the tree, and very quickly let me show you that you can just click on decision tree. This is how you add the nodes, you can add the branch, and first I want to show you how you can highlight the best strategy, and we are going to review that together. Now it is highlighted in green. So first decision node is whether or not to submit the proposal. You can say submit or don't submit. And that submitting the proposal will cost $5,000. If the proposal is submitted, then we encounter an event node showing a 50% chance of receiving the grant and 50% chance of not receiving the grant, leading to a net loss of $5,000. If he is awarded the grant, he then needs to decide whether to use microwave, cellular, and or infrared communication technology. And then, since he has to spend money on research and development, each of these three strategy nodes has an event node, strategy options has an event node representing the best case with the lowest research cost and or the highest with the worst case with the highest R&D cost that might be incurred. And you can see according to the best strategy, he should submit a proposal because the expected value of this decision is this value, $13,500, and expected value of not submitting the proposal is 0. Then this highlighted strategy indicates that if he receives the grant, he should pursue the infrared communication technology because the expected value of this decision is $32,000, and this is larger than the expected value for other technologies, which are $29,000 and $28,000. So the optimal strategy is to submit the proposal and use the infrared technology. And again, building this tree is very easy. You can click on decision tree, start with building the nodes, add a node, change a node, and it's very straightforward. Just click on help, user guide, and building your first decision tree. Now, I want to show you that before implementing the optimal decision to submit a grant proposal, as suggested by this analysis, it would be wise to consider how sensitive the recommended decision is to changes in values in the decision tree. For example, he assumed a 50-50 chance for receiving the grant. What if only a 30, 20, or 10% chance exists of receiving the grant? should he submit the proposal or not? Let me show you how easy you can build this strategy table using an Excel data table to analyze how the optimal decision strategy changes in response to two simultaneous changes in the probability estimate. So this is the two-way data table. This is essentially sensitivity analysis on the decision tree and on the decision choices we would make, and we have created this table by using the standard Excel data table. The formula is on W16. We have added this formula saying if the decision to submit a proposal is yes, then we should choose the best choice in K27, choosing one of those technology options, microwave, cellular, or infrared, and capture that value. And then you can see the table function is array inter. So let's review the table together. This makes it clear that this solution is relatively insensitive to the changes in probability of receiving the grant. Here you can see the probability is increasing, and the strategy that is still infrared. However, if the probability of encountering high infrared R&D cost increases, the preferred strategy quickly switches to cellular technology alternative. Therefore, as a decision maker, you might want to give closer attention to risk of changing these probabilities that you have assumed in your model before implementing your strategies. Now, instead of simply varying parameters, we can use the power of simulation to consider many more possibilities. So this is the next version, and again, this is available in the examples. When you install the trial version, don't worry about all the details, but I just want to review how you can actually benefit from these examples and all the power that is available to you. Here, you can see we have added numerous uncertain distributions for both the probabilities of certain event happenings as well as the cost associated with certain outcomes. We have built this table using several psi functions which allow us to better understand the decision with the highest overall expected value as well as a way to look at results by individual trials. Let me show you all the formulas. You can see on the right side. We're using the psi mean for calculating different outputs. Okay, now let's run one simulation. Click on Simulate, Run Once. We are going to focus on AA16. To close the rest of the charts, and I'm going to make it small. So here, there are 4 decision alternatives, and we have numbered them 1 through 4. You can see that while strategy 2 may overall have the highest expected value, that was only the case across 1/3 of trials. Fairly close behind is what was strategy 3. This tells us it may be worth looking into the distribution of results across each strategy to see if they're actually more comfortable with another strategy given potential downside in some outcomes. Okay, now let's go back to our slides. We're going to move on to our third topic. That is about how you can make best possible decisions in situations where you have risk and uncertainty. Here, we will use the power of optimization. Now let's talk about the optimization problems. When you want to define an optimization problem, there are 3 main components. Just a conventional optimization problem. We have to determine the decision variables. We have to determine the objective function and constraint. These are the 3 main components of each optimization problem. To determine decision variables, you can ask what factors are under our control. And then the next component is the objective function. We want to maximize our expected revenue, for example, or you want to minimize your total cost. You can determine the objective with asking what measure are we trying to optimize. And typically in the optimization problem you have constraints, and you can determine them by asking what restrictions limit our choice of decision variables. Now, since this is a problem in an uncertain situation, we have uncertain variables. We can determine the uncertain variables with asking what external factors are not under your control. So now, having this information, let's go back to our airline revenue management model. Let's turn it into an optimization model, still with the simulation. So we know that our uncertain variable, the external factor that is not under our control, is number of no-shows, number of tickets sold. This is the value that's under our control. So that would be our decision variable. And then here we want to maximize our expected revenue. So we are ready to define our optimization model, still with the simulation. But one important point is that the product that we are using is Risk Solver Pro. It only allows us to access Monte Carlo simulation capabilities and decision trees. To access optimization, we need to change the product. So let's click on Help. First option is Change Product, and you can do this when you have a trial version or you have a product. Instead of Risk Solver Pro, I'm going to choose Risk Solver Platform and click OK. Now you can see the ribbon gets updated, and we can see that this product allows us to perform conventional optimization, Monte Carlo simulation, simulation optimization, and stochastic optimization, which is beyond this topic here. But I will show you our YouTube channel set of videos that talk about the stochastic optimization components. So if you have a trial, you can do this yourself. Now let's take a look at ribbon. What has changed? So simulation model is the same. Now we have the optimization model components. If you recall, there are three components. We have the decision variables. If there's a constraint, here is how you can define your constraints, and then your objective function. You pick a cell with a formula. You want to minimize something or maximize something. And then you can see into parameters, the optimization is here, and so on. So first, let's define the number of tickets sold as our decision variable. Again, this is the value that is under our control. Just before that, if you recall, we define number of tickets sold as a simulation parameter. First thing I need to do is to remove that formula from that cell. Let's just replace this with 100. So select the cell that you want to define as your decision variable, and then click on Optimization Model, Decision, Normal. You can see C11, number of tickets sold, is now defined under optimization under our variable. So this is our decision variable. Now we want to maximize our expected revenue. To do this, let's select the expected revenue cell and then click on Objective, Maximize, Normal. You can see this is added under optimization under Objective in the Model tab. Okay, let's go back to Platform tab. Make sure we put the number of simulation back to 1. You can keep the trials on 10,000, and then you can see here, now we have other options for your optimization model. We are ready to solve this optimization model. So let's click on Optimize. This is called guided mode. It is a step-by-step help that helps you in your optimization, solving your optimization problem, and gives you information about your model, especially if you're not familiar with optimization concept. So click on Continue. Here it tells us what is the structure of this model, and if I click on Next Step, it will solve the problem for me, and it gives me that solver found the solution. Let's click OK, and here are the results. As we explored alternatives in the optimization, we decided that we should sell about 117 tickets. This is consistent with our parametric simulation trend chart, if you recall, that reflected the balance between no-shows and overbookings where we can earn the most revenue. This is an example of simulation optimization, and you can do much more using our tools when you want to optimize uncertain situations, and you can refer to our user guide to explore the stochastic optimization chapter. Now let's go back to our slides and review some points about the paybacks of risk analysis. Monte Carlo simulation helps you evaluate the impact of uncertainty in a business situation. The simulation approach is more realistic than give me a single number, with the goal of identifying the best decision involving multiple stage decisions and uncertain outcomes. At each stage, decision tree helps you develop an optimal strategy, and this is much better than ad hoc decisions as you go. And then simulation optimization helps you determine the best way to allocate resources in the presence of uncertainty. This will allow you to save money while hedging for risk. Now, just a brief overview of product line. We started with Risk Solver Pro in this session, and then we used Risk Solver Platform. And we showed you what you can do with Risk Solver Platform for simulation optimization. A more advanced product would be Analytics Solver Platform. Our Risk Solver products are by far the fastest Monte Carlo simulation products in Excel, often 10 times faster than competitor products. This matters when you are performing advanced analysis such as multiple parameter simulations or simulation optimization or what-if analysis with interactive simulation as we practice today. So this is still talking about simulation and decision tree. The whole product line contains a much broader area of analytics. So let me show you the full picture. It includes forecasting, text mining, data mining, simulation risk analysis, decision trees, and conventional and stochastic optimization. Analytics Solver Platform is a complete tool set for your predictive and prescriptive analytics for problems of any size. But still, there are more products. Our wide-ranging product line empowers you to perform analytics on the web and desktop spreadsheets, also web, server, and desktop applications in any scale. Now, if you're asking what is the next best step, register on our website for free. If you haven't registered, this will allow you to access the simulation tutorials, our downloadable user guides, like the ones we have been showing here. Furthermore, it allows you to download the free trial anytime you're ready. Try it yourself. During this trial period, you have full technical support. You can ask questions. Just give us a call, use live chat, or send me an email. So I'm going to share my email with you in the chat box. Okay, so it is consulting@solver.com. And just before answering your questions, let me show you that Frontline has a YouTube channel. We have uploaded a lot of training demo videos here on playlist. We have 30-minute training videos about risk analysis, Monte Carlo simulation, other products, optimization, and then also we have these videos on stochastic optimization. I'm going to share our YouTube channel address with you. Thank you very much. Again, remember, you're welcome to send any questions or comments to consulting@solver.com. Okay, bye for now.